Welcome to the Level 1 Quantitative Methods Summary video series. This video is a summary of the Quant reading on sampling and estimation. The idea behind a sample is straightforward. You have a population and you pull data from that population. If you have this population and you actually divide this into segments or strata, and then you pull a sample from each of these strata, then we call this stratified random sampling. Time series versus cross-sectional data. Time series is a sample of observations taken at specific and equally spaced points in time. Cross-sectional data is a sample of observations taken at the same point in time. Both time series and cross-sectional data, the random sample may be representative of the population we wish to study. Okay, some of you asked me about the central limit theorem, and this is very testable. I'll read this and give you a brief explanation, but then it is critical for you to practice lots of problems. Given a population described by any probability distribution having a mean mu and finite variance, the sampling distribution of the sample mean. So what does this mean? So you have a population, and let's say this population has a mean mu and some variance, and then you draw samples from this. The sampling distribution of the mean. So every time you draw a sample, the mean will be different. Okay, but can we say something about the distribution of the means, the sample means? We can, based on the central limit theorem. What does the central limit theorem say? That the sampling distribution of all these means, where the sample size is n, will be approximately normal. So we are saying that this distribution will be approximately normal. Now, without even knowing the central limit theorem, what do you think is the expected value of x bar of the sample mean? This is going to be mu. If you know that the population mean is mu, you don't know mu, but it's some number, then on average x bar is going to be equal to the population mean. That is intuitive. What about the distribution, the standard deviation of x bar? This is given by sigma, where this sigma is the standard deviation of the population, divided by square root of n. And what about this sigma x bar? So this is also called the standard error. Sigma of x bar is the distribution of the sample means. So be clear about this. When we say sigma x bar, we are talking about the distribution of the sample means. When we just say sigma, then we are talking about the population. So the population has a certain variance and standard deviation, and the x bar has a certain standard deviation. Sometimes you might not know the variance of the population. So what is a proxy for the variance of the population? You pull out the sample, and the variance of the sample then is a proxy for the variance of the population. And here we are using the standard deviation. This segment deals with estimating the population mean with some degree of confidence. So let's say you have a population and you want to estimate the mean. So you draw a sample. What is your point estimate of the population mean? Your point estimate will be x bar, where you pull a sample and then you find the mean of the sample and you say this is my best estimate of mu. But are you 100% sure that x bar is equal to mu? Obviously not. Your estimate then actually needs to be x bar plus or minus something. What's that plus or minus something? That is given by this expression. Z alpha over 2 is calculated based on your degree of confidence. If you want to speak with 95% confidence, then the z value will be approximately 1.96. If you want to speak with 90% confidence, then the z value will be less. 99% confidence, the z value will be more than this. And then the second term is the standard error that we just talked about, which is the standard deviation of the population divided by square root of n, where n is the sample size. If you do not know the population standard deviation, then you use sample standard deviation. And another point is that when you do not know the variance, then instead of using the z-stat, you use the t-stat. For large sample sizes, the z and the t will give you roughly the same answer. In terms of the estimate, so x bar is an estimate. The process used to come up with the estimate is called the estimator. These are some properties. It should be unbiased, efficient, and consistent. Make sure you remember these three terms. It's very easy to be tested on them. All right, I have talked about reading the z table. Let's also talk about reading the t table. Let's say that you are given n equals 21. The first thing to recognize is that degrees of freedom equals n minus 1. So degrees of freedom will be 20. And then let's say that you are told that the probability in one tail is 0.025. Then what do you do? So if you are given one tail probabilities, this is 0.025. So notice that here the probabilities on a t table are given right here. On a z table, the probabilities were in the middle. So there's a difference between the z and the t table. You look up the degrees of freedom, and this is your answer. What if you were given the following? What if you were told that you are doing a two-tailed test, and on a two-tailed test the significance is 5%, and then the table you are given is this? So this gets some people confused. If you are doing a two-tailed test and the significance is 5%, that means the 5% is divided between the two tails. So how much will be in each tail then? 0.025 or 2.5% in each tail. So even though the significance is 5%, but given that it's two-tailed, you would still look over here, because this 0.025 corresponds to the probability in one tail. All right. What should the size of the sample be? If you want a very tight confidence interval, then what you can do is increase the sample size. When you increase the sample size, what happens to standard error? It comes down because n becomes larger. Say you want to work with a significance level of 5% or confidence level of 95%, then the reliability factor is fixed. Okay, you can't do too much about your point estimate. That's simply the average of the sample. So the only thing that you have control over is the sample size. The larger the sample size, the tighter your interval. But does that mean you just keep increasing the sample size? There are some issues. The first question you ask is, how precise do I really need to be? The second is that if I take a very large sample, maybe I sample from more than one population, which is an issue. And often trying to get a sample that's too big will be costly. This is something I want you to read, and these things keep showing up. There are several challenges associated with sampling financial data. You might have a data mining bias, sample selection bias, look-ahead bias, time period bias. Make sure that even if you don't understand these in detail, you should at least remember the items shown on this slide.